Recording is rolling. It is Wednesday, October 2nd. We're about 15 minutes into class. You guys just watched a bunch of Paul Hewitt demos, mostly related to Newton's laws of motion. I'll upload those to Google Classroom also with this video. Your guys' projectile motion quizzes are returned to your folders. I think I forgot to mention that yesterday, but you guys, the same deal as with the linear motion quiz. If you want to do corrections, just find the ones that you missed, write out on a separate page of paper how to get to the correct solution, right? If it's graph, just draw the correct graph. And then staple that to your quiz and turn it into the grade tray. I can give you guys partial credit back for anything that you missed. If you're really stuck and don't know how to solve it, let me know. I can help you out. So today in class, we're going to go back, talk about that last Paul Hewitt demo that you guys just saw with the bed of nails. Then on this chapter 4 page, let's just hit this number 92, classic Atwood we're going to do here in a few minutes. And after that, you guys have some spring scales on your desk. I want to do a short lab that I've been wanting to do for a while. All right, so there's the agenda today. So flip my screen back over here. Here's the last Paul Hewitt that you guys just saw. Is this guy's on a bed of nails, right? Right on that bed of nails. Here, show of hands. How many guys have ever been on a bed of nails? Who's been on a bed of? Ooh, most of the class been on a bed of nails. Ooh, all right. Guys, what sounds better? Would you rather be on a bed of 1,000 nails or a bed of 2 nails? What sounds better? Let's go with 1,000, right? Now, what's the physics principle involved? Why 1,000 nails? Because why? Okay, so some do with surface area. Right? I think he may have caught it. He said, Paul's got more area. Okay, so some do with area, right? Okay. You guys think every nail head has, well, I guess the tip, you'd be on the tip, right? Has a little tiny area. And it got all your weight is on just one or two of those little tiny areas. That's a huge what? Guys, what is your weight's a type of force, right? What is a giant force on a little tiny area? What is force per unit area called? Starts with a P. Force per area. Pressure, right? Guys, what's some ways to quantify pressure, to measure pressure? Could you do, say, force per area? Could that be newtons per square meter, maybe? Newtons per square meter? Okay. How about you buy a bike pump from an American store? It's probably measured in, probably not newton per square meter, but what? PSI, pounds per square inch, maybe, or something like that. It's the same concept, just a little bit different way to think about it. Yeah, so if you have 1,000 nails, going back to this bed of nails, if you're on 1,000 nails, oh, your weight, which is just whatever it is now distributed over 1,000 nails. It's like, could be 1,000 times the area of one nail. Yeah, so that's a lot less pressure per nail. Yeah, so you can be safer. All right, and so back over here then. All right, so we're good, Paul Hewitt. I said I'll upload those demos so you guys get to see those again. Let's do number 92. You guys ready for number 92? I'll zoom in, read this together, and then draw this out and solve it. Okay. 2 blocks, got 5 kilograms and 3 kilograms, are tied together over a massless rope. Right? Sometimes it says a rope of negligible mass. Okay? Which, here, if I pause for a moment, think about it. If you did consider, what if the rope had pretty significant mass, especially compared to those weights? This would probably have a little bit different type of motion. Just a little side thought. I'm not going to solve that, but we did. More complicated. The rope is strung over a massless resistance-free pulley. Ooh, that's another simplifying assumption, isn't it? They're really spelling out the simplifying assumptions. Okay? This pulley has negligible mass and resistance itself. The blocks are released from rest. Find the following. Oh, the tension in the rope and the acceleration of the blocks. Hey, isn't that the 2 classic questions? What's the acceleration and what's the tension in the rope? Do that? All right, so let's go ahead and pick those right there. Right, guys, when am I picking up these puzzles? Monday? They're due on Monday? Right, of course, if you finish them early, you can turn them in early. That's okay too. But yeah, we got a due date on Monday, and we're doing number 92 right here, right now. I'll get you guys your quiz tomorrow, or your take-home quiz. Okay. So here's classic Atwood. Oh yeah. We're doing 4 and 5. I think tomorrow I'll take you guys through chapter 5. Yeah. So yeah, tomorrow we'll do chapter 5, forces in 2 dimensions. All right. So I got. Here you go. 5 kilograms right here. We got 3 kilograms right here. Boom, boom. Oh. All right. There's the setup. Okay. Right. Now, something about tension, something about acceleration. Ooh, do you think we're going to need some forces? Forces. We're going to go through Newton's second law of motion somehow. All right. So, guys, what's one force on this 5 kilogram mass? Yeah, okay, so gravitational force, it's weight, right? And how much weight is that approximately on Earth? How many newtons? Is that about 50 newtons, do you guys think? About 50 newtons? Okay. Where did I get that from? Is that from, is weight equal to mass times gravity field, right? I've got 5 kilograms mass. The gravity field could be 10 meters per second squared for Earth, rounding a little bit, usually do. Okay. Oh, hey, they didn't specify Earth, because if the physics textbook doesn't specify Earth, is that a reasonable assumption to say we're probably on Earth? Do you guys think that if you took this to the moon and released it on the moon, there'd be a different acceleration and a different tension? Yeah, I think there would be. So let's assume we're on Earth. That's a reasonable assumption. How about what's the weight of this 3 kilogram guy right here? 30 newtons. Okay. And ooh, should I make an arrow vector that's maybe a little bit more than half of the 50 newtons? Right, half of 50 would be 25, a little bit more than that, it's 30. It's about 30 newtons right there. 30 newtons. Okay. So 50 newtons versus 30 newtons. Look, it's a long arrow vector versus a shorter arrow vector. So, okay. Now, guys, those two forces right there, remember, are the external forces that's driving the system to go either clockwise or counterclockwise, the two-block system. Okay. Okay. There are some other forces. They're just internal to that two-block system. Oh, guys, what's another individual force on this 5 kilogram block? It's not on a surface, so I'm not going to call it normal. The tension, I'll call it tension, right? Right. So you guys think tension is probably pulling straight up. Okay. Oh, and how big should I make this tension? Between what and what? Yeah, between 30 and 50, right? Okay. Do you guys think that, especially if this pulley, here, let me add a little bit more story to this pulley, right? This pulley, I bet it's maybe like fixed into the ceiling, possibly, something like that. If that pulley is massless, frictionless, do you guys think this one string can have just one tension in it? So it'd be the same tension acting on both blocks. And overall, the large block is going to be accelerating down and the small block is going to be accelerating up, right? Just like your lab. So I need the net force to also be consistent with that. So I'm going to draw some tension force that's, okay, it's the same tension force on both. No, it's the same tension force. And it's more than the 30 newtons. Look at that, more than 30 newtons, but also less than 50 newtons, right? Is it? So if you draw everything to scale, I think it's pretty close to scale. Right? You guys want to guess the tension is probably roughly 40 newtons, right? Probably not exactly, but it's pretty close. When we get an answer at the end, tension equals so many newtons. Let's see if it's yeah, approximately 40 newtons. If it is, then probably in good shape. Okay. All right, guys, good so far with the setup. All right. Now at this point, you might remember last few days we've been solving these. I've been telling you guys there's 2 different type approaches to get to the answers. What I prefer to do myself is called a whole system approach. Okay. But that's in contrast to solving the entire thing with a system of equations, which we're going to need maybe later anyway to solve for the tension. Okay. So here's what I'm going to do. I'm going to kind of shuffle back and forth just to show you 2 different ways of thinking about this. Whole system approach, I can use Newton's second law of motion. Net force on the whole system equals the mass times acceleration for that system. F equals ma. That's Newton's second law of motion. Okay? And I can think about it as the 2-block system altogether. Now, I could go plugging and chugging right here, but hang tight, because here's where I'm going to divert away and come back to this. Okay? The other way you could set this up and start this, which if you take physics in college, you might have a physics teacher that prefers the system of equations method. Okay? So I'll call this a system of equations. And from there, you can go point of view 3 kilogram block and point of view 5 kilogram block. Okay. So each block you could set up its own individual equation, which is still going to be Newton's second law of motion, F equals ma. I should say net force. Net force equals mass times acceleration, but it'll be for each block individually. Right. Let's go ahead and set up these equations. Right. So for the 3 kilogram block, guys, what is the net force on the 3 kilogram block? Would it be this tension up and then this weight down? Should I add or subtract those 2? Subtract, because they're saying opposite things. This one says let's go up. This one says let's go down. Subtract. So if up is positive, then this net force would be the tension force pulling up, which we don't know yet, we're solving for, minus the weight down. Well, I know it's 30 newtons, so I'll just go ahead and call it 30 newtons. Right? Now that's a 3 kilogram block. I'll go ahead and do that. Right? It's going to be accelerating. Well, we don't know yet either. So that's 2 unknowns. Because if you have only one equation with 2 unknown values in it, is that solvable at that point? No. Maybe you can make a graph and get like a bunch of possible combinations of solutions, but you can't solve it in one directly. But what if you bring that in combination with this 5 kilogram block over here? Let's make a new equation. Now we're going to focus on this 5 kilogram block. Okay. Oh, guys, what is the net force on the 5 kilogram? Should it be maybe the difference between 50 newtons and the tension? Right, the difference is subtract. Now here I'm going to change the direction. I'm going to call it down positive because it's going to be accelerating down. Right, so I can have a positive value acceleration for each block. So I'm going to say 50 newtons down minus the tension resisting, which we're going to solve for, right, is equal to a 5 kilogram block accelerating at, well, again, I don't know, but what I do know is it's the same as this acceleration. Well, one's up, one's down, but I've got each of these equations oriented to the direction of the motion of the block. Okay. Now, guys, 2 independent equations with the same 2 unknown variables. Could you solve it? Could you just pick up from there and solve this whole thing if you wanted to from this point? Tension and acceleration? Could you do maybe a substitution or an elimination or maybe even a matrix if you wanted to? There's 3 different methods. Okay, you could solve it from here. Okay? This is the system of equations approach. Okay? Now, like I said, I'm going to shuffle back and forth. All right, you guys ready to go back to the whole systems? Okay. All right, I'm going to leave this to the side. We'll come back to this later. And I'm going to actually first solve this with my own preferred approach, which is the whole system. So if I think about this instead, now this is a different way to think of it, as a 2-block system, then would the tension be internal or external to that 2-block system? You guys think internal? It's just holding the blocks together? Okay, so that would not be an external force. So this net force, I'm not even going to consider the tension. Right? The external forces are these 2 right here. And if one's pulling clockwise, one says, no, let's go counterclockwise. Should I add or subtract those 2 forces? Yeah, I'm going to subtract. Let's do 50 newtons minus 30 newtons. Okay. So if you add them together, they might have something more to do with maybe the tension in the string holding the pulley up. We don't care about that. It's not. All right. So, guys, how much total mass is being moved around? Is it 5 and 3 kilograms? Right? Guys, remember, mass is a scalar, doesn't have a spatial direction to it. I can just add them up and say 5 kg plus 3 kg. It's going to be, okay, overall accelerating some value. Right? Now, of course, each individual block accelerates a different direction, one up, one down, but they have the same magnitude of acceleration. There's an overall acceleration. Okay? So I have a 20 Newton net force driving 8 kilograms to accelerate. Right. Oh, good. Hey, guys, good. I think I should have mentioned before, since we've gone through a few of these at this point, if you can stay a step ahead of me, that's a good sign. Right? If you can figure out what line is coming next, or if you can stay a few steps ahead, it's always a good thing. Okay. Of course, when I give you your take-home quiz, I'll know for sure if you can solve these. Okay. We're 1 algebra step away from getting the acceleration. Guys, what's the 1 algebra step? Divide down 8 kilograms. Okay. So acceleration is whatever 20 newtons on 8 kilograms is. 20 on 8. I'm looking at 2.5. That's the number on my calculator screen. Guys, that's 2.5 what? 2.5 meters per second squared. There you go, because that's an acceleration. Okay. I got a question about this earlier today, so just to clear this up, anybody needs a reminder how this works. Okay. Remember, meters per second could be a speed. That's just how fast are you going, kind of like miles per hour, meters per second. Okay. Meters per second squared is you're changing your speed, maybe speeding up. So if I point a radar gun at this falling block, say like every second, it's picking up another 2.5 meters per second. So if I count 1, 2, 3, 4, 5 seconds, go like 2.5, 5, 7.5, 10, 12.5, right? It's picking up 2.5 meters per second every second. All right, you guys good? Okay. Now, actually, that was question B. The fact they asked the tension first, I'm thinking the text was probably leaning toward that system of equations method, but we got the acceleration. Okay, you guys good? We got the acceleration. One block's going accelerating down, the other is accelerating up that much. All right, now we're ready for this right here. So now, if you had started with this method, remember you have two equations and two unknowns. But since we just did the whole systems approach, we actually know this acceleration, don't we? We actually know this, right? Right. So from our point of view, it's, starting from this whole system, we got the acceleration. Now we just want the tension in the string. You don't actually need to do both blocks. I'm going to solve it for both blocks to show you it's the same tension regardless of which block you pick, right? But just pick your favorite block and then say what's the Newton's second law of motion as applies to that single block, and then it'll get you the tension. All right, I'll do both, show you guys this works out. So I'm going to pick up from knowing what is the acceleration as, okay, so I got 3 kilograms here. This could be 2.5 meters per second squared. And then over here at 50 newtons minus the tension is 5 kilograms times 2.5 meters per second squared. Okay. All right, let's do more math. 30 newtons. 3 times 25, is that like 7.5? That'd be newtons at that point, kilogram meter per second squared. And over here, 3 newtons minus the tension force. That 12.5, I think, newtons. All right, I think that's true, right? So a little bit of math, a little bit of cleanup. All right, now we're going in for the finish. Tension force equals, tension force equals. Okay. So from the point of view of the 3 kilogram block, you can just add over 30 newtons. Does that give you 37.5 newtons? That? Is that? Right. From the point of view of the 5 kilogram block, well, okay, I could add the tension force and subtract over the 12.5 newtons. That would isolate tension force equals. That's what's 50 minus 12.5? 37.5. And then the unit is also newtons. Hey, look at there. It's the same tension, which I told you it was going to be. It always works out that way. The massless frictionless pulley and the rope has negligible mass. Yeah, that'll be the case. Same tension force. All right. So while you guys are trying to write that, just for recap, review. 2 approaches to solve these classic Atwoods. You could set up a system of equations, look at each block individually, 2 equations, 2 unknowns. You could do a substitution method, which I did not do here, because instead I picked the other method, which is I did a whole system approach. I looked at the 2 block system and then got the acceleration first. So we got that. Went through Newton's second law of motion. Okay. The net force is the difference between the weights. The total mass is the 2 masses added together. Okay. And once you got the acceleration, well, now you can pick your favorite block and pick an equation, right? Plug in the acceleration and solve for the tension. And either block you pick, you'll get same tension. All right, all good? All good? All right. So I got one last item on my agenda, and that's this spring constant lab. You guys have on your desk, you guys got a quarter page? Everybody got a quarter page? Oh, yeah. Yeah, we'll do this tomorrow. Yeah. Okay. All right. So you guys got a quarter page. Guys, write your name. Write your name on the quarter page. And call this spring constant lab. Okay, spring constant lab. You guys got that? Right. You guys have a bunch of spring scales on your desk. I've got most of them here. I think I'm just short a blue one. That's all right. So spring constant. Ooh. Right. This here, I showed you guys this poster a few weeks back. You guys remember Hooke's law? Hooke's law? Right. I was telling you guys this is how these spring scales work. Is that if you apply a force to stretch the spring, it's going to stretch some amount. And actually, that's a direct relationship. Right? If you put on twice the force, it's going to stretch it twice as much. Right? But each spring is a little bit different. Like this green one, I put on a tiny force, it stretches really easy. This gold one is really stiff. I put on a force, it's really hard to stretch that one. You guys remember that? So each spring is a little bit different. You can see just looking at them, right? Some springs are kind of skinny, some are really thick wire. Right? So, but there's this linear relationship. That's Hooke's law. F equals kx. Guys, what does the K stand for? Spring constant, spring constant. And that's what I want you guys to figure out is what is the spring constant for each of these spring scales? So there's 6 scales. Let's set up some constants. Here, I'm gonna turn this off. Give me some trouble there. All right. So we got a blue scale, or you guys have a blue scale. There's a green scale. There's a brown scale. Red, white, and gold. Right? Figure out what is the spring constant for each of these scales. How stiff is each spring? Right. Little hint, I did actually rank order those, so all the numbers should go in order. Right? There should be an order to these. Okay. And I'm going to demo one of these for you guys to show you exactly what I'm looking for. Okay. So let's say I pick the brown scale. This is kind of a medium type scale, right? Pretty versatile. Okay. Okay. All right, so, guys, are you looking at the side that says grams or the side that says newtons? Which one tells you force? Newtons. Newtons is force, right? Okay, so here, I'm going to do some math out here. Okay, let's do Hooke's law goes F equals KX. Some textbooks throw a negative sign there to talk about the restoring force. I'm not going to worry about that. Okay, so I'm just going to say the application force. So, I can apply any force I want, and it's going to tell me how much force that is. And also the spring is stretched by some amount. So let me pick a random force. Let's say 8 newtons. Get the 8 newtons, it stretches that much. I can go up to 10 newtons for the spring scale. That's okay too. Right. I'm going to pick 8 newtons. Just pick a number. About 8 newtons force. Okay. I'm going to solve for what's the K for the brown scale. Okay. And there's some particular stretch distance that's associated with pulling 8 newtons. I wonder what that stretch distance is. Let's find out. I got a ruler here. Got a ruler. Okay. Are you guys using inches or centimeters? Centimeters. And we'll convert to meters later on, but we'll start with centimeters. Guys, here's another question I've been getting all day today. Where do you start the 0 on the ruler? Should you start back here and measure the entire length of the spring, or should you start at the 0 Newton mark and only measure the amount that it stretches? Which one is correct? And if you're looking at this poster, it gives away right here. Here could be unstretched. You could have a compressive spring, although these aren't compressive. We have stretchy springs. You guys see for the unstretched, I'm putting a dash right there, and I'm measuring the stretch distance relative to the unstretched location. You see that? Okay. So if this is starting at 0 newtons, that's my 0 point also on the ruler. So I'm going to measure out to 8 newtons. What is that distance? And it looks about, I'm going to call it 4.1 centimeters. Okay, is that right? 4.1 centimeters? 4.1 centimeters to stretch 8 newtons. Oh, okay, well, or if I apply 8 newtons, it stretches at 4.1 centimeters. Okay, okay. Okay. I want to solve for the spring constant. So divide that over, what is 8 on 4.1? That's like 1.95. So the spring constant for the brown scale is 1.95. Now that's newtons per centimeter is what that is. Now, usually though, if you're trying to compare a bunch of different spring scales, or you open up a physics textbook, the unit tends to be in newtons per meter. So let's go one more step. I'm going to throw in some railroad tracks here. We're going to do a unit conversion. I don't want newtons per centimeter. I want newtons per meter. Is that okay? Newtons per meter, right? So how do I go from centimeters to meters? How many centimeters are there in 1 meter? Huh? 100? 100, right? Same thing as how many cents in a dollar. Right? Something to do with 100. Should the number 100 go on the top or the bottom? The top. 100 centimeters is equivalent to 1 meter. Remember the theory of why this process works. That's a fraction equal to 1. Numerator is the denominator. Centimeters cancels. So the spring constant on the brown spring is equal to 195 newtons per meter. That's the answer. What does that mean? Suppose I see this spring's really short. It's a really short spring. What if I had a really long spring that was like way longer than this, but it was equally as stiff? So if I was blindfolded and I was pulling this and I was pulling that longer spring that was equally stiff, I couldn't tell the difference because they both feel the same. It's like, well, it's the same force, it's stretched the same distance. Okay? But I have a really long spring. And suppose I stretch the really long spring by 1 meter. You guys got that? I got a really long spring that's exactly the stiffness, and I stretch it 1 meter beyond its equilibrium. How much force would that take to stretch it 1 meter? 195 newtons. Ah, you guys see that? You guys see that? All right. So you guys have the Brown scale. Call it 195 Newton per meter. There you go. There's your bingo free space. And another hint that I'm giving you guys is these are ranked order, so they'll all be a different number, but yeah, so all the numbers should be in order. Right? All right, I'll walk around, help you guys out. Guys, when you finish that, toss that in the grade tray. That is our wrap on today.